All right, guys, we're going to talk about torque. This is section 7.3 in the book. We're going to come back to moment of inertia after this, but let's talk about torque, okay? Now, what is torque? Let's start with writing down the equation, then we can talk about it. But actually, let's talk about an example. Okay. Torque is the tendency of something to spin. It's how well you can make something spin. Okay. And you have to, first of all, apply force in order to get something to spin. Think about a door. A door is a really good example, right? A door has a fixed axis of rotation, and um, it takes a certain amount of force that you have to apply to the door in order to get it to rotate. Now, watch this video of me opening a door. Here are some other examples of torque. Using a hammer to pull out a nail, also pounding a nail in with a hammer, and taking the tire off of your car. Have you ever had a flat tire? Then you're gonna know what torque is. All right, let's start with the problem here, and then we will explain what torque is. Okay, so we're trying to basically start with the problem, an application, and then we'll talk about the theory of what's going on here. Okay. Now, you probably already know that oftentimes wind can push a tree down, right? The base of the tree is fixed, and a wind blows, and the top usually has a bunch of leaves, and so there's a big force created by drag on the tree. Okay, so we can model a pine tree in the forest as having a compact canopy at the top of a relatively bare trunk. Wind blowing on the top of the tree exerts a horizontal force and thus a torque that can topple the tree if there's no opposing torque. Okay, suppose the tree's canopy presents an area of 9 meters squared to the wind, centered at a height of 7 meters above the ground. Okay, these are reasonable values for a forest, for tree in a forest. Yeah, it sounds pretty reasonable. Pine trees are over 7 meters tall. Now, is that really true? Imagining a tree. Okay, suppose a tree's canopy presents an area of 9 meters squared. Okay, so it's about 27 square feet to the wind, centered at a height of 7 meters. Okay, so 7 meters, that's about 21 feet tall. Sure, that seems reasonable. Okay, if the wind blows at 6.5 meters per second, what is the magnitude of the drag force on the wind, of the wind on the canopy? Okay, assume that a drag coefficient of zero point 0.5 and a density of air of 1.2 kilogram meters per squared. Okay, part B, what torque does the force exert on the tree measured about where uh measured about the point where the trunk meets the ground? All right. Well, there is a lot to unpack in this problem, so hey, let's get started. I did too much shading here. All right, we're gonna have to add some numbers here. Okay, well, maybe a little less detail would have been better. All right. But anyways, I'm gonna draw this line over here. And what did the problem say? The problem said that the wind centered at a height of 7 meters. Okay, so 1, 2, 3, 4, 5, 6. Oh, look at that. That's seven right there. Woo! Each each square is a meter. Wow, that's not bad. Okay. We did a great job drawing this pine tree, and then we've got about nine meters squared. Okay, so 9 meters squared, so maybe 3 by 3. Okay, so let's draw our pine tree as a triangle here. Okay. And we want the area to be 3 meters squared. So, oh, I guess I drew my pine tree a little too big, but we can make it. Yeah, so 3 by 3. Let's do that. Okay, so here's 3 times 3. That's 9 meters squared. Okay, so it's basically 9 squares. Well, we'll say that our pine tree is kind of skinny. So here we'll do our pine tree like this, basically. Here's 1 square. Okay. So this will be, we're gonna do a pixelated pine tree. Okay, here's 8 squares. Yeah, there's 8 squares, and then there's the top of our pine tree. Okay, so I'm saying each square is 1 meter. Okay, and so then to the center here. So I don't know. I don't know what I'm doing here. All right. Well, anyways, the area of our pine tree here. Let's draw another pine tree over here. Okay, that's about pine trees are kind of shaped like this. Okay, so the area of our pine tree is 9 meters squared, and then I'll this is my area of my pine tree. Okay, all right. So this is important because we're going to calculate the force of drag. So maybe this was a maybe you don't want to be too artistic when you draw this because then you can't label everything. But you know what? It's fine. Okay. So and then to the center of our tree here. We'll call this 7 meters. All right, that's 7. All right, we drew our picture. We have a nice comic book style tree over here, and then this is the one that we need to actually do calculations with. All right, so first things first, let's calculate the force of drag. All right, so we need to get our drag force here. We're going to call that D. Okay, the force of drag is equal to 1/2 times the coefficient of drag times rho, the density of air, times the area of the thing times the velocity squared. Okay, so this is our force of drag, and um, this is the force that's going to apply a torque. Okay, we talked about drag a little bit before, but now let's talk about torque. Okay, so we can pretend that this drag force is centered at 7 meters above the ground. Okay, so we're going to simplify this even further. We're going to say, all right, I'm going to draw this proportionally now. So 1, 2, 3, 4, 5, 6, 7. Okay, so here's my pine tree. Okay. And the force of drag is going to be applied right here. So this is our drag force. Okay. And then the ground here, this is where this thing is basically going to rotate against. Okay. So we've got our force of drag. And okay, here's our force of drag. Then we've got our moment arm here, R. This is the height uh, to the center of the tree right here. Now, torque. Let's talk about the equation for torque. We're going to use the Greek letter tau, and that's going to equal our torque, which is going to be R, a vector R, cross a force. So it's R crossed F. All right. Now, we have two vectors pushing against each other. So one vector here, R, is pointing this way. Okay, so we've got our vector here, R. That's our vector R is pointing from the rotational part up here to the top, and then our force is pointing against that. Now, torque is a vector, okay, and it's perpendicular to these other two, okay, which means that it's coming out of the page, okay. Well, now, in the videos, I talk about the moment arm here, R. And R is the distance from the pivot point. So this is how far you push on the door, basically, right? How far are you away from the hinges. And then F is how much force you're applying. Okay. Now, let me tell you a little story about torque. Imagine a young Dr. Neutron, and there was uh, uh, a young lady that I had asked out on a date. I was in college and I was pretty excited and I was pretty nervous. And so I tried to open the door and I pushed on the wrong side. I was so nervous. I didn't look at the door carefully. I don't want to say I was awkward when I was younger, but when you're a freshman in college and you have an important date, sometimes you might feel a little awkward. And so I pushed on the wrong side of the door, and it was a pretty heavy door, and I ended up having to push really hard, and I was a little bit embarrassed. I don't think the date went very well, but I felt awkward after that, and so maybe that was a time where torque had an effect on me emotionally because I felt a little awkward and I felt kind of silly. So. Moral of the story is on your first date, definitely think about torque when you open the door. I don't know if you should think about torque on a date. Never mind. All right, let's get back to the problem here. Okay. So, um, basically the force that we come in here, times the distance of the arm is going to create a torque. And torque is the tendance, how easy it is to make something spin. The higher the torque, the easier something's going to rotate. Okay. So, if you listen to my story about my first date with bad torque, then you too will understand what I'm talking about. But basically, if you push on the wrong side of the door, you're not going to get a lot of torque, and so you won't be able to open the door. Let's talk about the video with the nail where I use a hammer to pull a nail out. Okay, so let's say here is my the nail. Okay, it's going in here, and it's stuck in a board. Okay, and so I'm trying to get this nail out here, and basically my hammer is going to come in here, and it's going to apply some torque to the nail. Okay, so here's my rotation spots. Okay, and we're gonna apply a force perpendicular to this. Okay, and it's gonna pull the nail out. Okay. and it's going to apply some force over here. So we'll call this force on the nail. Okay. And this arm here, we'll call it Rn, the distance to the nail. Okay. Well, here's the thing about torque. Okay. Just like force, all the torques have to be equal. Okay. So that means the torque on the nail has to equal the torque on the handle. Okay, now the handle, right? The handle is, let's say, it's much, much longer. Okay. It's way, way longer than the over here to the nail. Okay. And let's say that this is maybe, let's get my here. Okay, so this is about 3.5 centimeters. Okay, that's what you got down here. So we'll call this, we'll say RN is 3.5 centimeters. Okay, and a hammer, I'm gonna say, wait, what did it, oh no, I did it in inches. Oh, shoot. It's not inches. Okay, no, it's, let's say, it's about nine centimeters. Oh my goodness. Oh, see. This is what happens. Okay, 9 centimeters. That's the moment arm of the hammer here. Okay, and then I'm looking at my tape measure, and I'm thinking that the handle of the nail, it's about yay long, and so that's yeah, it's about 30 centimeters. Okay, so this is 30 centimeters over here. Okay, and I don't know, is my handle? Let's say it could be 10 centimeters. Let's go with 10. We're just gonna round that off, okay? Yeah. Now, let's say that I apply up here the same amount of force it would take to pick up a full stein of beer. So let's say that's about 25 newtons. Okay, let's say double that because I'm really gonna crank hard on this nail. Okay, so. What am I gonna do here? All right, so the distance here, this is R handle. Okay, that's the R handle. And then the torque that I apply up here, okay, this is, let's say this is 50 newtons. 50 newtons. And I'm applying it from over here. So this is 50 newtons. Okay? So, and we want to know what's the force over here that you're going to get to pull this nail out of. Because see, what's going to happen is apply a force over here, and this arm is smaller, and so it's going to multiply your force. So, okay, it's kind of like a lever, actually, right? It is actually a lever. But let's talk about levers, okay? 'Cause this is really interesting. So I'm going to write down the equation for torque here. So this is the force on the nail, which is what we're interested in, okay? And this is going to be times, yeah, here's the force of the nail, okay? Cross the, yeah, this is the, well, actually, let's just do it this way, okay? Before I talk about this, okay? Uh, Torque is a cross product, okay? And so what you end up with is it really is R times F times sine of phi. And that's the angle between the force that you apply here, okay, and your moment arm. Okay, now sine of 90 degrees is equal to 1. Okay, and that's going to give us the maximum torque. Okay, that's our maximum torque. So sine of 90 here, okay, that's like this angle right here. Okay, now if you come in at a different angle, you're going to get less force, right? If you come in, say, maybe pushing down on your hammer like this, or maybe the wind's coming down like that, you're going to get a lot less force. Okay, try it. Try different angles of applying force. The maximum for torque that you get is when R, your moment arm, and your applied force are perpendicular when they're at 90-degree angles. And so what you end up with, sine of 9 equals 1. And so really, we're going to use the expression torque equals R times F. Okay. Ooh. Man, write that down on your card. Torque equals R times F. Ooh, this one's important. You know what? Where's my card? I'm making a card up here. Boom. Here's my next card. All right, I'm gonna write torque on here. Torque. Okay, torque is equal to the vector torque. I'm gonna write that there. R cross F, okay? But the magnitude of the torque is equal to R times F times sine of phi. Oh, you know what? I feel like I'm gonna make a little diagram here. Yeah, here's my rotational point. Okay. I'm gonna draw a little arm here. Okay. And this is R. That's R. Okay. And then the angle here, okay, between my force and R. Here's R. This is F. Okay. So this angle here, that is phi. And I'm gonna put F up here. This is F and this is R. Okay. And there's my angle. Here's my equation if and so at phi equals 90 degrees, okay, we're gonna call this max torque. Yeah, I'm torque maxing. Or as I like to say, I'm physics maxing. Ho ho! That was like a million aura. Wow. Okay. Hmm. Anyways, I'm putting this on my card. So down here back to the hammer example, okay? We're doing the physics of a hammer, okay? So, all right. We got the torque of our nail, okay? So that's going to be Rn times the force on the nail is going to equal the distance, the moment arm of the hammer, so RH times F of the hammer, okay? And if you have a nail that's stuck here, okay, maybe let's go with 50 newtons. That's about two full steins of beer or liquid, probably water. All right, here's our. And when I say a stein, I mean like the big cups in Germany. And if you go to Oktoberfest, right, then they might fill this full of beer. I'm gonna draw a beer here. Here's my beer. I noticed that some people have beer as their status on Discord. I don't know what that means. I don't know if beer is a status, but here's the bubbles. All right. So here's my stein of beer. Okay. And if I just hold this in my hand, this is I measured it is 22 newtons. Boom, that's how much it weighs. Okay. We're going to talk about another example of torque. Actually, it's called Stein competition. I'll show you what that is in a minute. All right, so let's put in what are we going to do here? We want to find the force on the nail, right? If I apply 50 newtons of force with the hammer, what am I going to get to pull this nail out of? Because that's really what I'm interested in, and that's what hammers are good for. Is one thing is pulling out a nail. Okay, so here, this is the force on the nail. It's going to be the moment arm of the hammer times the force on the hammer divided by the moment arm of the nail. Sorry, I can't help with siblings. Exclamation point. Oh, yes. Okay, so I'm going to put in my numbers here, and I've got the moment arm of the hammer. I've got the force I applied to the hammer, and then the moment arm of the nail here. Okay. And I'm actually going to put this into meters. Okay. Although it doesn't really matter, because it's going to be the same ratio. So here, since it's centimeters, you can just leave it as centimeters. All right. So let's go and throw this into, let's go throw it into MATLAB and hopefully we get something good here. Hopefully the force is bigger. All right, here we go. All right, so we're gonna put this into MATLAB and we're gonna see what force we get. We're gonna have 30 divided by 10 times 50. Okay. Oh, would you look at that? Oh my goodness. We actually, I felt really nervous about this equation. I was like, is it going to give us a bigger number? All right, but let's look at how incredible this is, okay? Because what happened here is that I applied 50 newtons of force, okay? And this moment arm was longer, okay? And on the nail, okay, the force that you end up with is 150 newtons. Wow. That is pretty cool. Okay. Uh, so that's like it's a multiplication factor of three here. Okay. So what do we what did we learn from this? The longer you make your lever here, okay, and the shorter you make this, the more force you're gonna get. And I think a famous scientist once said, I'm thinking it was Archimedes, if you give me a lever, I can move the world. Wow, I feel like this is kind of amazing. I've never done this calculation before, but man, my mind is blown. All right, let's talk about the final thing that we're gonna do about torque. All right. So, basically what you need to do is you need to get something that weighs 5 pounds. Okay, this is about 5 pounds, okay? And I want you to hold it out at shoulder level here. So here's your, hey, this is, you can use a weight or you can fill up a beer stein and put liquid in it, okay? And you're gonna basically hold this out at arm's length. Here's your shoulder, okay? So your shoulder needs to be straight. Okay, here's me. Yeah, maybe you're at Oktoberfest. I don't know. But you gotta stein a liquid here, 5 pounds. It's about 5 pounds for a full glass of liquid that they sell at the Oktoberfest, okay? And basically your arm is, yeah, it's about a meter. I think mine. Let's measure the length of my arm here. All right, how far is my arm? Let's get some data here, man. See, that's I'm an experimentalist, and so I'm gonna measure my arm here. Yeah, you need to. Let's put this on camera. Okay, this is muy importante. Okay, we need to collect the data. How are we gonna collect? I got a measuring tape here. Okay, so see. Okay, so when I hold a my stein of liquid over here, it might be beer. Okay, to my shoulder. Okay, I'm gonna go right here. What do we got? Oh, how many centimeters? Is that? I was thinking my arm is like a meter long. Is it 1 meter? No, it's like half a meter. Is that? That doesn't seem right. Okay. If I go from fingertip to fingertip, something is amiss here. All right. Now that's gonna be, yeah. Okay. So yeah, fingertip to fingertip. If you do that from one fingertip to the other, okay, that's actually supposed to be your height. Okay. Now, when I do this fingertip to fingertip here, we're getting data for this problem here. Okay. So I'm putting my fingertips out and on my tape measure, I get, oh, look at that. See? I get about 6 feet. That's pretty cool. Except in real life, I'm not actually 6 feet. Okay, so that proportion, it kind of works. I'm actually more like 5'9". Yeah, my son who's 5'10" likes to remind me of that frequently. Okay, so I'm 5'10". That's gonna be no, I'm 5'9" actually. That's gonna be 69 inches. Okay. My son is he's 5'10" and that's about 70 inches. Okay. So in centimeters, I'm gonna say that I am 175 centimeters tall. Good to know. Okay, and my arm, measure my arm here. Guys, we did a lot of experiments today. Like we actually went outside and measured them. That's pretty exciting. Good. So right here to my shoulder, it's about, yeah, I'm looking here. Okay. So that is, I'm gonna go with 65 centimeters. Now it's actually 64. All right, we're gonna go with 64 centimeters. Okay, we got some data now. Okay, so for me, from right here, okay. Oh, and then the beer. I'm not beer. I mean, whatever, whatever the liquid you choose to put in your cup. And if you're ever wondering what kind of cup I'm talking about, let's take a look here. I actually got this at a castle, Berg Hohenzollern. Now this is actually smaller than you get if you go to the Oktoberfest. I've never been to the Oktoberfest, but I hear there's it's really good food at the Oktoberfest. But so from about the handle to over here, okay, and I was drinking water out of this earlier. That's what the liquid is in the bottom. See, it's water. All right, but from right over here, okay, to the center of my cup, that's gonna add another 10 centimeters. All right. So the length of my arm to my shoulder was uh it's 65 centimeters plus that extra width from the cup. That's going to put me at 75 centimeters. Let's do some calculations. Okay, because at certain times of year, if you go to Oktoberfest, they often will have a competition to see who can hold one of these steins the longest with their arm outstretched. Okay, so this is 75 centimeters. All right. And we've got this is about 22 newtons of force. Okay. It's 5 pounds. Okay. That's pretty significant. Okay. Now, the competition is you have to hold this out as long as you can. Okay. And so, and usually then there's, whoever's left then wins a gift certificate. Okay. All right, so let's calculate the torque on this. Basically, we've got our torque is equal to R times F. And let's see, this force, so my force is going down here. That's 22 newtons, and the angle is 90. So it's 90 degrees here. So I got sine of phi here. And remember, okay, sine of 90 degrees equals 1. That's its maximum. Okay. It really, that's the maximum. So these are perpendicular to each other at 90 degrees. Okay. So I've got the distance here is 0.75 centimeters times 22 newtons. Okay. So 22 newtons. Okay. And so this is going to give me a torque. All right, let's throw it. I'm excited about this. I've never actually calculated the torque on your shoulder for one of these competitions. This is actually pretty exciting for me. Okay, so 0.75 times 22 newtons. Okay, so that is a torque of 16.5. And yes, and the units on this are Newton meters. Okay, that's the units of torque. Wow. All right, this is really exciting. So the torque from a stein of beer held out straight is about 16.5 newtons. You know what? We're just going to call this 17 Newton meters because there's a little bit of uncertainty in my measurement. All right. Wow. I feel like we've learned a lot today. What did we learn? Well, we know the weight of one stein is 22 newtons. Okay, and I measured this actually. And the torque on one Stein held out at arm's length is 17 Newton meters. Okay, I guess you could say we learned some important constants today. All right, let's finish this. Let's finish this pine tree problem. Okay. So, part A asks us to find the force of drag on the pine tree. That's the first problem. Okay. So, let's write down the equation for drag. Okay. So, drag we'll call it D, and it's going to be 1/2 C times rho times A B squared. So, drag is a strange force in a sense because it is completely velocity dependent. And so that makes it hard to come up with a lot of different solutions unless you're at terminal velocity. And that's a velocity where you can't fall any faster because the force of drag equals the force of gravity. And so those two forces are balanced and then you're falling at a constant velocity. But that usually happens at a pretty high speed. Unfortunately, it would be lethal for humans falling out of an airplane, but squirrels, on the other hand, can easily survive falling out of a tree because they're so fluffy. So, if you ever wondered why squirrels are so fluffy, it was actually an evolutionary defense that keeps them alive in case they fall out of trees. They actually fall out of trees a lot. If you have ever spent some time watching squirrels, they'll just fall off of a telephone wire or just fall out of a tree. Um, and probably helps if they land on grass, but anyways, all right. So it says in the problem the coefficient of drag is 0.50. Okay. And we need to calculate the force of drag so that we can find the torque on the tree. All right, the problem also says that the density of air is 1.2 kilograms per meter cubed. Okay, so now we've got C, we've got rho, and then A, the problem says that the area of the tree is 9.0 meters squared. And I may have said meters cubed. That was wrong because that would be a volume. Okay, then the last thing here, we need the velocity of the air, and it says the wind blows at 6.5 meters per second. Okay, so now the problem says, assuming the drag coefficient is zero point 0.5 and the density of air is 1.2 kilograms, all right, what is the magnitude of the drag force uh, of the wind on the canopy? All right, well, we've got all of our numbers here. Okay, so we can basically just plug this into our equation, and then we're gonna put it in into MATLAB, and so I'll just write it out here. Okay, the force of drag is gonna be 1/2. I don't know why this thing's not focusing. All right, 1/2 times 0.50. Okay, then times the density of air, and this is a coefficient, so it does not have any units. Okay, the density of air is 1.2 kilograms per meters cubed, and it's funny to think that air actually has weight, but it does. If you ever go scuba diving, you might know that an empty scuba tank actually an empty scuba tank weighs less than a full scuba tank. Okay. Um, and so I've always found that really interesting. But, anyways, now let's put in the area here. So the area is 9.0 meters squared. And then the velocity, okay, our velocity is 6.5 meters per second squared, 6.5 meters per second. And then that should be squared there. All right. So part A is I think pretty straightforward. We just had to look back and get the force of drag here, but that wasn't too bad. And actually calculating the torque's really not that bad either if you know how to set up the problem. Okay. And that setting up the problem is really kind of the key here. All right, so I'm going to put this into MATLAB. Oh yeah, excuse. I use MATLAB for everything. It is my calculator. You can do a lot with MATLAB. Okay, 1/2 times. I'm just gonna say um 0.50 times 1.2. The only thing I wish you could do in MATLAB was put in the units because in Mathematica you can, and I find it very convenient. 6.5 meters squared. Okay, so that is going to give me a force of, it looks like the drag force is going to be that is 114 newtons. Oh, okay, 114 newtons. And so that's about the force of holding 4.5 steins of beer. Okay, so we're gonna say that this translates to 5 steins. It's my unit, stein. I don't know if I should say that on YouTube, but I already said it. Can't take it back. All right, 114 newtons. I think we did it. Let's plug it in and okay. And it is a force, and so what did we get? 114 newtons. We are correct. Oh, I guess they said 110 newtons. All right. What torque does the force exert on the tree measured about the point where the trunk meets the ground? Okay, so yeah, let's draw a picture of this, okay? Um, and basically we can think about it. We're gonna, normally a pine tree is something like this, okay? Maybe the wind is blowing on it. Here's our pine tree, okay? And it's kind of bent over like this, okay? But, here's our pine tree. The wind is blowing on it, right? The wind is going this way, okay? But this is kind of complicated. And so we can basically make a model of this and just say, all right, we have this is a 7 meter rod, okay? And so here's 7 meters. That's how tall this thing is. And all of the force is applied right here. So here's my axis of rotation, okay? And so just like a door, the tree wants to rotate. Now, trees can only extend a certain amount of torque, and then the tree is going to break. Okay, and usually trees are strong enough to survive the wind, hopefully. Okay, so here's our force. It's the force of drag, and this is 114 newtons. I'm going to keep that there, and then R, that is my moment arm R, and so the torque on this thing. Okay, it's going to be R cross D, and I can also write that as a vector. It's equivalent to R times D times sine of phi. Okay, and phi is this angle here. And I'm going to say that this is 90 degrees. Okay, so this is 90 degrees. And at 90 degrees, sine of 90 degrees is equal to 1. Okay, so we can really just write this. The magnitude of the torque is R times D. Okay, and the length here is 7. Okay, so this is going to be, yeah, this is going to be 7 meters. Okay, and then times the force. So times 114 newtons. Okay. And so then our torque is going to be about 700, maybe 800. All right, let's throw in a MATLAB. I'm saying it's about 800 newtons. Yeah, but we will calculate the value. All right. So, 7 meters times 114, 798 or 798 Newton meters, and that is torque, right? A Newton meter. It's also interestingly, it's kind of the same as if we did work. Work is also Newton meters, but that's a joule. But in torque, we want to keep it in Newton meters, so that's very specific. Okay, so this is 800 Newton meters. All right, and so we finished the problem here, and we talked about torque. We discussed all the principles. Hopefully you watched the experimental video where I actually used used the hammer, and I show you in this video how to calculate torque from the hammer and the advantage that torque gives you when you use a hammer. So, all right. I think we accomplished a lot here today. Thanks for watching this video. Thanks for watching this video.
Thank you, like and subscribe down below.